All right, picking up where we left off, here's some hints that they have for balancing equations. And I gave you the hints that I had. They recommend changing the coefficients of compounds before changing the coefficients of elements. So you would do CO2 before you did oxygen. And what I said was, leave oxygen and hydrogen for last. And out of the two, whichever one is the element, leave for the last of the last. And why does it always do that? Okay. If you have a polyatomic ion, such as carbonate, sulfate, nitrate, and they're on both sides of the equation, treat them as one unit. It's a lot easier to count the polyatomic ions than say, okay, this one is 1 carbon, 3 oxygens. If you have 1 CO3 on both sides, that part's balanced. And at the end, always check. I always have people who balance an equation and say, oh, it's balanced. I'll look at it. It's not right. And when I check, the oxygens will be off, the carbons will be off because they change one side and they forget to change the other side. So here we're doing a combustion of butane, C4H10, plus oxygen to give us carbon dioxide and water. So the way I was doing it, telling you start with carbon first. You can see on the left you have 4 carbons. So now we're going to add 4 carbons to the right by putting a 4 in front of the CO2. So now we have the carbons balanced. The next one we're going to do is hydrogen, because we have hydrogen and oxygen left, and oxygen's by itself, so we can leave it to the end. So the hydrogens, we had 10 on the left. To get 10 on the right, we put a 5 in front of the H2O. Now if you look at the oxygens, we have 2 on the left, and at the right we have 13. 4 times the 2 in CO2 is 8 oxygens. 5 times the 1 in the water is 5, so together is 13. Well, if you look on the left, we have 2 oxygens. We don't have an even number. But we could put 13 halves, or what I do is 6.5, whatever 13 is divided by 2, on the left. So now technically it balances, but you can't have, in this case, 13.2, an improper fraction. So you have to get rid of that. You multiply everything by 2. And you just multiply the coefficients, so you end up with 2C4H10 plus 13O2 goes to 8CO2 plus 10H2O. And then, again, at the end check, you have 8 carbons on both sides, 20 hydrogens on both sides, and 26 oxygens on both sides. So now it's balanced. Okay? Everybody all right with that? Yes? No? No?
Just
Okay. Hopefully I'll have, these lectures are recorded, so I just ran the other one through YouTube the other day, so I'll probably post it today or tomorrow sometime under chapter 3, because it takes them a closed caption, and I got to let it run overnight. So here we're going to do one. The barium hydroxide plus perchloric acid goes to barium chlorate plus water. And right now I am going to pause it because, okay, again, let's look at this carefully. You see we have 2 polyatomic ions here. We have OH, the hydroxide. We only have it on one side of the equation, so we're only going to count that as O's and H's. But we have the ClO4, the chlorate, we have that on both sides. So I'm going to start with the chlorate. So how many do I have? On the left, I have 1, and on the right, I have 2 ClO4s. So the first thing I would do is put a 2 in front of the HClO4. So now I have the ClO4s balanced. Well, then I'm going to go back to the non-oxygen and non-hydrogen, at least barium. I have 1 on both sides, so I'm fine there. So now you look at the hydrogens. On the left, how many do I have? How many do I have on the left? How many do I have here? 2. How many do I have here? 2. I have 2 from the OHs, 2 from the HCl4. So I have 4 hydrogens on the left. I got 2 on the right, so what do I have to put in front of the H2O? 2. Now I'm going to look at the oxygens, not the ones in the ClO4s, because I've already balanced that, the ones that aren't in the ClO4s. So on the left, how many do I have? 2. 2 times 1. 2 outside the parentheses multiplies each subscript. So I have 2 on the left. How many do I have on the right? We're not counting ClO4s. 2. This 2 multiplies everything. So it multiplies this and this. So 2 times 1 for the H2O. So I have 2 oxygens on the right. So now we're balanced. All right. You treat the ClO4s, yeah, don't count them again. Don't count them the second time. And I can't get the thing to advance. So you see, there's not counting the ClO4 oxygen. They're separate.
A question.
Yes.
Why do you wait to do the hydrogen and oxygen for last?
Just experience that it's usually easier because you usually have something like water, and it's usually easier to add a coefficient there. So after you get everything else balanced,
Okay.
just from experience, hydrogen and oxygen usually fall into place at the end. So you can see the first thing I do is balance the chlorate anions, the ClO4s, and then, well, they did the hydrogens because the ClO4s, they did the hydrogens. We didn't have to do the bariums. And then they did the oxygens. So here's another problem. Butyric acid is being oxidized, or in this case, metabolized. So metabolism is actually an oxidation reaction, just like burning. If you look at it, okay, as the products of combustion, the carbon dioxide and water, butyric acid, that's what forms in rancid butter. So if you ever have butter that goes rancid, spoiled, you get that really nasty odor, that's what it is, butyric acid. So again, we're going to start, well, we got carbon, hydrogen, and oxygen. I would say you start with what? Carbon. 4 on the left, what do I put on the right? 4. Subscript for carbon here is 1. This 2 goes with the oxygen. There's a 4. All right, hydrogen on the left I have. So on the right I have 2 I have to put in front of the water. Okay. So on the left, how many oxygens do we have? 4. How many do we have on the right? 4 times 2, 8. And CO2, 4 times 1 for the water is 4. 8, 4 is 12. So I have to have 12. I don't want to touch the butyric acid because I've already balanced the carbons and the hydrogens. So butyric acid has how many oxygens? 2. So I need 12 on this, on the left side. So I'm going to subtract the 2 from the butyric acid. That leaves me how many left? 10. I can put a coefficient in front of the oxygen. What number times 2 gives me 10? There we go. And we're balanced. So we use butyric acid for something? Well, it's not a random equation. Yeah, I mean, you can metabolize it. I mean, it's in butter and different things, but we get a lot of it. When butter goes rancid, you produce more and more of it. But we metabolize it into carbon dioxide and water. So there's the process again. If you do it step by step, most of the time it'll be pretty simple. As long as you keep remembering the coefficients multiply every subscript. So like in water, 4 multiplies to 2 for the hydrogen to give you 8. 4 multiplies to 1 in the oxygen. So you gotta remember, if you don't see a subscript, it's 1. So we need to have this, and again I kind of said at the beginning of this chapter, we have 1 cup of sugar plus 2 cups of flour goes to 1 dozen cookies. Essentially I wrote the same thing as a chemical equation. And if I just said sugar and flour gives you cookies, what are you going to ask me? How much sugar, how much flour? And then in the end, you want to know how many cookies you're going to get. So that's what a chemical equation tells you. It tells you the number of units that you're going to put together and what you're going to get out. So it's the same thing as baking. Baking is chemistry. We're just going to change the terminology because if we use cups, then that would have been too easy, so we have to confuse you somehow. So we're going to change our terminology. Remember at the beginning of the semester, I did that big presentation. Chemistry has its own jargon. Don't get psyched out. Don't get psyched out. Nothing more than baking. So we're going to talk about the mole. I forgot to bring my mole. I got the stuff mole for the lab coat on. But the mole in chemistry is a unit of counting. So if I said to you, bring me a dozen eggs, you'd all bring me 12. So you know a dozen means 12. A dozen donuts, you're going to bring me 12. Okay. A mole stands for 6.02, should be 6.022 times 10 to the 23rd objects. So if I say bring me a mole of oranges, you'd bring me 6.022 times 10 to the 23rd oranges. You'd probably fill up this whole room and then some with oranges. That's a lot of oranges. Or if I said you had 6.022 times 10 to the 23rd apples, you'd have 1 mole of apples. Okay. So if you had 6.022 times 10 to the 23rd avocados, how many avocados would you have? 1 mole. Or maybe in the case of avocados, it would be a guacamole. Yes?
So,
Oh, come on, it was funny. Yes?
it's a very specific number. Is there a reason?
Yes, there is, and we'll get to that. It's a very specific number. So a mole, like we said, is a counting group. It's a definition of a certain number. A mole is defined as the number of atoms in exactly 12 grams of the carbon-12 isotope. And it turns out, if you measure that, you come up with what's called Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd. So that's where that number came from. Okay. So next Tuesday, if you want to bring me 1 mole of chocolate chip cookies, you're more than welcome.
You funded program.
If I could fund that many cookies, I wouldn't be here talking to you right now. Okay. So we know 1 mole is equal to 6.022 times 10 to the 23rd objects, whatever those objects are. So again, we have an equality. Remember conversions, we have an equality, we can make 2 conversion factors. 1 mole of objects is 6.022 times 10 to the 23rd objects. I don't know why it's showing up like this. And 6.022 times 10 to the 23rd objects is 1 mole. I think when it saved it in Smartboard, it screwed up the exponents. So here we have typical human body. Contains roughly 30 moles of calcium. A, determine the number of calcium ions in 30 moles. So for A, again, like all conversions, we start with what we know. What do we know? What were we given? 30 moles. What do we want to know? We want to know how many calcium atoms. So, and those are the objects. The calcium atoms are our objects. So, we're going to multiply it by some conversion factor. Remember, we want to get rid of the moles, so the moles have to go on the bottom of the conversion factor. On the top, we'll go calcium atoms. So 1 mole contains how many calcium atoms? 6.022 times 10 to the 23rd. So now we have everything. So we just 6.022 times 10 to the 23rd times 30. That's 18.022 times 10 to the 25th. 1.802 times 10 to the 26th, I believe. 18.066. That's 1.06 times 10 to the 26 calcium atoms. For part B, we want to know the number of moles of calcium in a sample of 1 times 10 to the 20 calcium atoms. So again, what are we starting with? We're starting with the number of, no, part B, what do we know? We know the number of calcium atoms. 1.00 times, what was it, 10 to the 20th calcium atoms. And we want to find out the moles. So here, we're going to have the atoms on the bottom and the moles on the top of their conversion factors. So 1 mole, again, is 6.022 times 10 to the 23rd. So it's whatever that comes out to be. Push the page down button. 1.66 times 10 to the minus 4. Oh, this should be 20. This should be 26. Okay. And this is 1.66 times 10 to the minus 4. Oh, it's going to work. Yeah, okay. I see what you're saying. Okay. So we can convert atoms into moles, moles into atoms. So I'm going to write, we're getting right now into what we call stoichiometry. I'm going to write the stoichiometry roadmap, which is on Blackboard for you. So I'm going to pause that right here. Okay, so now you have the stoichiometric roadmap on the board. It says it's in Blackboard in that chapter. We're going to kind of work our way through this roadmap. And like any roadmap, you think of it as a city roadmap, we have streets and we have stops along the streets. So where we are at the top here, particles and moles. We just did that. Add particles, in this case, the problem with the calcium, particles were calcium atoms. So if you go to atoms, to moles, you follow the arrow this way, and it says you divide by Avogadro's number. When we had the 30 moles of calcium, we want to know how many atoms. We're going from moles to atoms. So we multiply by Avogadro's number. So the whole thing of stoichiometry is figuring out where you're starting, where you're ending, and then follow the streets and do what the streets tell you to do. So if you look at the roadmap, you know we can go from particles of A to moles of A. We can go from moles of A to grams of A. We can go from moles of A to moles of B, moles of B to grams of B, grams of B to moles of B, particles of B. So we can go all over the place. We can't go directly from grams of A to grams of B. You know, it's a map, one-way streets. If I want to get from grams of A to grams of B, I got to go from grams of A to moles of A, from moles of A to moles of B, from moles of B to grams of B. So there is no shortcut for that. So once you figure this out, stoichiometry really becomes easy. When I worked in research, we'd spend, a couple weeks planning a whole synthesis, a whole bunch of steps. The stoichiometry part of it was the last 10 minutes. My down button keeps messing up. Okay. So we're going to talk about molar masses because it's on the stoichiometry. What the heck's a molar mass? How can we do it? You didn't tell me what it was. The molar mass, and it's that fancy M there, of a substance is the mass in grams of 1 mole of a substance. What's that mean? Well, remember, we said carbon-12 was used to define a mole. It's the number of atoms in carbon-12. So 1 mole of carbon-12 contains 6.022 times 10 to the 23rd carbon atoms. And if we know how much a carbon atom weighs, we can figure out what the total weight is in grams. By definition, the mole of a carbon-12 atom is exactly 12 grams. So the molar mass is equal to its atomic mass. Wow. That's kind of lucky. Well, it turns out, without doing all the math, the molar mass of a substance is equal to the same thing as its atomic mass. So, we did formula masses and molecular masses, you do CO2, you add a carbon, 2 oxygens, and it was 44.01 AMU. Well, it turns out that a mole of carbon dioxide weighs 44.01 grams. It's the same number, it's just instead of AMU, it's in grams. So when we're talking about AMU, we're talking about molecular and atomic scale. When we talk about molar masses, we're talking about stuff you can weigh out, grams. So if I said, what's the atomic or the molecular mass of water, you would go to the periodic table, 2 hydrogens times 1.008, 1 oxygen is 16.00, you add them together, it's 18.02 AMU. Now go in the lab and measure out a mole of water. Now you have to deal with molar masses. So you'd go in there, take your balance, put your beaker on there, and you would add water until it weighed 18.02 grams. You go, hey, I got a mole of water. So in effect, 1 mole of atomic mass unit is 1 gram. So they're numerically equal. Well, that's great, because you already know how to figure out AMU masses. We did that before. So you don't have to do any conversions to convert to change to molar masses, except change AMU to grams. Yes? Are you with me? Okay. So here is their version of interconverting mass, moles, and number of particles. Feel free to use it. I like using the one I wrote on the board that I put here because to me, it's just a much simpler roadmap. This one you go back and forth different times, but whichever one makes you happy, that's the one you can use. So determine the number of moles in 10 grams of naturally occurring carbon. So naturally occurring means you're not dealing with specific isotopes, we're dealing with the average atomic mass. Before we even look and start putting numbers into equations, people start jumping off there. Look at the roadmap. What are we starting with that we know? 10 grams of carbon. So we're starting off with, on this map, where? Grams of A, because we're given grams. So we're going to start here. What are we looking for? The number of moles. So we're going to end up at mole of A up at the top here. So, what will we start with on top? We want to end up with how many moles of carbon. So I'm going to multiply that. What's on the top here goes on the bottom here. Grams of carbon, mole of carbon. 1 mole of carbon is how many grams? No, we don't need Avogadro's number there. We need the molar mass. What's the molar mass of carbon? 12.01. Look on your periodic table. It's the same as the AMU. So there. Now I have all the numbers. Because what does the map say? To go from grams of A to moles of A, I divide by the molar mass. I'm dividing by the molar mass. Whatever that comes out to be. B says the mass is 0.905 moles of sodium chloride. So I'm starting for B, what was I given? I wasn't given the mass. What was I given? For B, the number of moles. So I'm going to start at moles of A. What do I want to find out? The mass. So I want to find out the grams of A. So I'm going in the other direction. And no, it doesn't matter what I call it, if I started at A or B, because it's a symmetrical map, which is why I like it. So for the bottom one, I say, okay, I have 0.905 grams of NaCl. Oh, moles, I'm sorry, moles of NaCl. I want to find out how many grams of that is. So I'm going to multiply it with moles on the bottom, because I want to get rid of it, grams on the top. 1 mole of NaCl, what's the molar mass? Well, read it off the board, 58.44 off the slide. How do we get 58.44? We looked at the periodic table. Sodium is 22.99. Chlorine is 35.54. You add them together, you get 58.44. Now you have your numbers. 0.905 times 58.44. If you look at your map, to go from moles of A to grams of A, it says multiply by the molar mass, which is what we're doing. So let's see what the answers are. So the first one, we end up with 0.8326 moles of carbon. Bottom one, turns out we have 52.9 grams of sodium chloride. Now, what I always said when you do your calculations, look at your answer to see if it makes sense. So we know the molar mass of carbon for A is 12. 12.01, we know it's 12 grams per mole, and we're starting with 10. So our number, our answer should be more or less than 1. Less. 10 is less than 12, so we don't have a complete mole, we should have some part of a mole. And we have 0.8326. So if you did the calculation backwards, you'd have a number greater than 1. Similarly for B, you're not starting off with a whole mole. And we know a whole mole of sodium chloride weighs 58.44. So if we don't have a whole mole, it's got to weigh less. And sure enough, it only weighs 52.9. If we had done the calculation backwards for some reason, we would have ended up with more than 58.29. So look at your answer to see if it makes sense. Okay, determine the number of water molecules and the number of H and O atoms in 3.26 grams of water. So what are we given? So we're given grams of, according to the map, grams a day. What do I want to find out first? What am I asked to find out? The number of molecules. So what would that be on the map? No. What are molecules? Particles. So I'm going to end up over here. How many streets do I have to go down? According to the map. 2. So I'm going to have 2 conversion factors. So I start with 3.26 grams of water. I want to know how many molecules of water. Well, you can see by my map, and that's why I like this one, because it's more obvious on this one than it is in the one in the books. I can't go directly from grams to particles. But I can go from grams to moles. I got to go up first. So where I'm going to get moles of H2O Grams are on the top, they come to the bottom, grams of H2O. So now I'm at moles, I'm at this stop. Now where can I go? Particles, in this case the particles are molecules. So I go to molecules of H2O divided by moles of H2O. So now I come back and put the numbers in. 1 mole of water, what's its molar mass? It was 18.02, I believe. Come over here. 1 mole of water is how many molecules? 6.022 times 10 to the 23rd. So if I look at my math, starting in grams of A to go to moles of A, I divide by the molar mass. I'm following the arrow. I'm dividing by the molar mass. Then to go from moles of A to particles of A, I'm going to multiply by Avogadro's number. Well, I'm multiplying by Avogadro's number. So now I have all the numbers. Now it's just plug and chug on your calculator. And boom. End up to be 1.09 times 10 to the 23rd water molecules. The second part of that, yes?
I'm sorry, the 103.26 is just,
I just used, when I put this, just make sure that this stays in the numerator. So when you look at it, you know it's in the numerator. See how they do it? They don't put it over 1. And it's kind of, sometimes people read that quickly, and they'll put it in the denominator and divide by it, and they get the wrong answer. Or if you do it on a worksheet or on your piece of paper, first the number you write, you tend to write it right on the line. Then the next one you write the fraction up, and then oh, it's on the bottom. No, it's on the top, which is why I always put it as over a 1. So the second part of the question was, how many atoms, hydrogen atoms? Well, you have these many molecules of water. How many hydrogens are in water? 2. So if I have that many molecules, it would be twice that for the hydrogen atoms. Because there's 2 for every molecule. So I take the 1.09 times 10 to the 23rd and multiply it by 2. Now the oxygen atoms would be the same, because there's only 1 oxygen atom per water molecule. So you get the same answer for the oxygen. So is this making sense? Yes? No? No?
Not a lick of sense.
Okay. Where?
I mean, I'm just, like, I gotta go back and review it, like, that's just how I kind of learned, but it's just a lot,
It is a lot. But if you break it down step by step, it's not a lot. That's why if you follow the map, if you step by step.
The only thing I'm not getting is, you know how the answer came up to 1.09 times 10 to the 23rd
Yeah.
H2O molecules? How are you getting the 1.09? Because I don't think I'm doing that right.
3.26 times 6.022 times 10 to the 23rd divided by 18.02. I believe that's what it comes out to be.
Share order of operations.
Yeah, this one wouldn't be too bad. These are where people run into problems when you divide in scientific notation, you have to put it in parentheses. Usually multiplication. Did you try doing it on your calculator? Well, this is the time to practice and make sure you get these answers. B, they gave you that many molecules and they wanted to know how many grams. So for B, we're going just the opposite direction, starting with molecules of carbon dioxide and ending with grams. So the first step, what are we going to do? We got to go to moles, so what are we going to do? Divide by Avogadro's number. So you see the first step there, 1 mole of CO2 over 6.02 times 10 to the 23rd. So we're dividing. So now we're at moles of A. To go to moles of A to grams of A, we're going down. What are we doing? Multiplying by the molar mass, which is 44.01 over 1. Hey, you do all the plug and chug on your calculator, and you get 5.79 times 10 to the minus third grams of CO2. So that's a small number. It's a small weight. But we have less than a mole. Because a mole, we know, is 6.02 times 10 to the 23rd, and we only have times 10 to the 19th. So when you go back and you go over these slides again, please take your calculators out and run through the calculations, make sure you get the numbers they are. If not, you're doing something wrong with your calculator. And I can help you maybe because it's like 8 gazillion different types of calculators. I have to find all the buttons. Sometimes I can, sometimes I can't. So we're going to take a brief hiatus from the stoichiometric roadmap to look at empirical formulas for percent composition. Now we did empirical formulas. That's the least ratio. The hydrogen peroxide was H2O, so its empirical formula is HO. Remember that? The lowest reduced one. So if you have 3 hydrogen peroxide molecules, you have Christmas. Yeah, you got that, right? Ho, ho, ho. All right. So, here we have a compound that is 30.45% nitrogen. And what was it? Oxygen, 69.55. What is the empirical formula? Well, the way to do this is assume you have 100 grams of sample. So if I have 100 grams of the sample, how much of it is nitrogen?
30.45%.
Yeah, but how many grams is that? 30.45 grams. So how much oxygen do I have? 69.55 grams. Now, elements combine to form compounds, not by weight, but by moles. So I have to figure out how many moles of that. So how do I figure out, I got 30.45 grams of nitrogen, how many moles is that? How do I convert it to moles? Divide by the mole mass. You go to the stoichiometric roadmap, grams of A to moles of A. So I'm going to divide the nitrogen by its molar mass, I think it's 14.01, and the oxygen by its molar mass, which is 16.00. So if I do that, I end up with 2.173 moles of nitrogen. And 4.347 moles of oxygen. Now, we're going to do what we call normalization, is where we take the smallest number and divide everything by the smallest number. So 2.173 divided by 2.173 is, thank you. We divide this by 2.173, that's 1. 4.347 divided by 2.173 is approximately 2. So now I know how it goes together. 1 nitrogen, 2 oxygens, NO2. So that's the empirical formula. Okay? The trick to that, strategy to that is assuming a 100-gram sample, because that makes working the percentages very easily. Or it should be easy, it shouldn't be an adverb. Well, we set empirical formulas. Well, molecular formulas are different. If you remember before, acetylene, C2H2, its empirical formula was CH. Benzene, C6H6, its empirical formula was also CH. If I say the empirical formula is CH, how do you know which one you have? You don't. Unless I tell you one more ingredient. So how, in practice, do we do these percentages? Where do we get these percentages? Well, we do a technique called combustion analysis. And in combustion analysis, we burn it. And there's a little diagram right there. You have this instrument and you flush oxygen through it, and you have a sample in a furnace, and you burn the sample, and it sweeps all the byproducts through this instrument. And you have some material there that absorbs water, and you have material there that absorbs carbon dioxide. So if I'm doing a sample that has carbon, hydrogen, and oxygen in it, if I weigh the H2O absorber before and after, the weight it gains is water. The hydrogen in that water came from the sample. Similarly, the carbon in the CO2 came from the carbon in the sample. Now, where did the oxygen come from? Well, there could be oxygen in the sample, but we're also sweeping oxygen through. We're adding oxygen to sweep the sample through. So we're not quite sure where the oxygen came from. But there's a way to determine where it came from. So they're talking about glucose, which contains carbon, hydrogen, and oxygen. Here, we're burning glucose, 18.8 grams. And we find out we produce 27.6 grams of CO2 and 11.3 grams of water. I want to know how much carbon and how much hydrogen. So I'm starting off with the mass of carbon dioxide. So I'm starting off on my road map here with grams of A. I want to figure out how much carbon. Now, carbon is not the same as carbon dioxide, so I want to figure out how many grams of B. So to get the carbon, and I'm not going to write it down, we start with the mass of carbon dioxide, so that's the grams of A. If I look at the road map, I got to go where? Moles of A, so I'm going to what? Divide by the molar mass. If you look at the next step, 1 mole of CO2 over 44, so I'm dividing by the molar mass of carbon dioxide. I go to moles of A, I got to go to moles of B. And I said their coefficients. Now, this isn't really an equation, but how many carbon atoms are in CO2? 1. So I have 1 mole of carbon for 1 mole of CO2. So that's 1 to 1. That works out real well. So now I'm at moles of B. I want to go to grams of B. What do? Multiply by the molar mass of B. So now I multiply by 12.01 grams of carbon per mole of carbon. Do all of that, I get 7.53 grams of carbon. Remember, we started with 18.8 grams of glucose. So I know the carbon is 7.53. Similar calculation for hydrogen. Starting with 11.3 grams from the water. We go to moles of water by dividing by the molar mass. But now we go from moles of A to moles of B. How many hydrogen atoms for water? 2. So now instead of 1 to 1, it's 2 to 1. So you get 2 moles of hydrogen per mole of water. And then final step, we multiply by the molar mass of water. And if we do all of that, now we end up with hydrogen, 1.26 grams. If we add this, it's 8.79 grams total. But our sample was 18.8 grams. So I'm missing some. What must it be? The oxygen. Before we said we couldn't tell where the oxygen came from, but now we can. If there was no oxygen in the sample, this would have added up to 18.8. Or 18.8. So we're going to subtract these. Well, actually, I need 8.8. And we end up with 10 grams of oxygen. So now we have the weights of the carbon, hydrogen, and oxygen. Okay? What was the next step? We have to figure out how do they combine. They don't go together in grams, they go together in moles. So I have to convert these to moles. So now I have to take the carbon, divide it by its molar mass, 12.01, the hydrogen, 1.008, and the oxygen by 16.00. And if I do that, I think the carbon comes out to be like 0.63, the hydrogen 1.26, and the oxygen 0.63. So what's the empirical formula for glucose? If I normalize it now, divide each of these by what's the lowest number? Okay. 0.63 by 0.63 is 1.26 by 0.63 is 2. 0.63 divided by 0.63 is 1. So the empirical formula is CH2O. If I shoot this into mass spectrometer, I can find out that the molecular weight of glucose is 180. Or the molar mass is 180. So now I want to figure out the molecular formula. What does this add up to be, CH2O? Carbon 12, oxygen 16, hydrogen 2. 12, 16, and 2. 30. So this weighs 30. I said it weighs 180, right? So 1 unit weighs 30. So how many units do I have to have? 6. So I have 6 of these. So if I multiply by this by 6, I get C6, H12, O6. That's the molecular formula for glucose. And here's how we figured out the oxygen. And there's how we would do the number of moles. And then you normalize it by dividing everything by the lowest number. CH2O. And the molar mass I said was 180. So 180 divided by 30 is 6. That tells us there's 6 CH2O units of glucose. So you come up with C6H12O6. Questions? It looks a lot more complicated than it is because there's several steps.
Pretty simple. You know.
Well, yeah, it's pretty simple. Yeah, pretty much everything in life is pretty simple if you know the steps, okay? I've never flown an airplane, but I imagine if I knew the steps, I probably could. And practice, obviously you gotta practice. You just don't walk in there and fly an airplane. So, here we have, we're starting with benzene, 5.50 gram sample. And we burn it, we get 18.59 grams of CO2 and 3.81 grams of water. So again, we're going to go through the same thing. Figure out how many grams of carbon, how many grams of hydrogen. And here are all the molar masses that you need to know. So the mass of carbon, again, grams of A to grams of B, divided by the molar mass of A, 1-to-1 carbon for CO2, then multiply by the molar mass of carbon, 5.073 grams of carbon. Do the same thing for water, except remember that there's 2 moles of hydrogen per 1 mole of water, and we end up with 0.426 grams of hydrogen. Add them together, and it's 5.5 grams. We started with 5.5 grams. So how much oxygen's in the sample? Nothing. What's 5.5 minus 5.5? 0. So we don't have any oxygen. We just have carbon and hydrogen. All right. So now we have the grams of each. We have to figure out what? How do compounds, atoms, join to form compounds? Not in grams. Moles. We have to figure out how many moles of each. So we have to take the weight of the carbon and divide it by its molar mass, 12.01, and the hydrogen divided by 1.008. And if you do it, it comes out essentially the same number. So its empirical formula is CH. And remember we said that was the same thing for acetylene. Now, mass spectrometer tells me that benzene weighs 78 grams per mole. Well, a CH unit weighs 13, 12 for carbon and 1 for hydrogen. So 78 divided by 13 is 6. So I have 6 CH units. So the molecular formula for benzene is C6H6. Now acetylene, I said, was C2H2. So its molecular weight would be 12 and 2. Oh, I'm sorry, 24 and 2, 26. So 26 divided by 13 is 2. So it had 2 CH units, so it would be C2H2. So unless you know the molecular weight, you can't give you the molecular formula. You can give you the empirical formula, but you have no idea what the molecular formula is, unless you know what the molecular weight is. I know it's a lot, but there's really no hard math, and it's all, I say basic algebra, it's probably even more basic or a word, more basic than basic algebra. We're not rearranging any equations. The stoichiometric roadmap tells you exactly what to do. Okay. We're going to stop there because that's where I want to stop.